Hello and welcome back to my channel. In today's video, I'm going through the PCB design for the audio amplifier circuit. If you remember, a few weeks ago we did a schematic capture for this circuit and we're using the MAX9768. So you can see on the screen now I've got the fully assembled board, so it's all been delivered. I do need to assemble it, but let me show you the PCB design now and go through the main aspects. Now that the introduction is out the way, it's time for me to tell you about this video's sponsor, PCBWay. A huge thank you to PCBWay for sponsoring this video. The PCBs that I'm designing in this video will be manufactured and assembled by PCBWay. They have advanced capabilities of manufacturing up to 60-layer boards with seamless turnkey manufacturing and assembly. An added feature, it doesn't cost an arm and a leg. On the screen now, you have the PCBWay website where you can easily get quotes for PCB manufacturing and assembly. So I'm just going to quickly go through the process for ordering PCBs. So obviously you need to define the size of the board, how many PCBs you want to order. So let's say 70mm by 70mm as a random number. And then you have various options that you need to select. Obviously this will depend on the PCB that you are making. You have customization options, so you can make your PCB in different colors. And then finally you press the calculate button and it gives you a cost of manufacturing for the board itself. So you can see a board that is 70mm by 70mm and ordering 5 quantities with 2 layers will only cost $5 for the 5 boards. Obviously the shipping cost will depend on the country that you live in. So please make sure to go to PCBWay.com to check out the services because they really do make the engineer's life a lot easier. So MAX9768 is a 10 watt mono class D speaker amplifier, and it has the potential to do digital volume control using the I2C channel that's on the part. So what I'll do now is go through some of the main aspects of this board. Hopefully this little PCB will give us high quality audio with minimal power consumption, as class D is supposed to be very efficient, but we'll need to see what happens. There are definitely some improvements I could have made to this board after reviewing it 2 weeks after I ordered it. But first of all, I want to make sure it works, and then I'll make a video later to see if we can improve the performance of this PCB at all. So as I said before, this is a 10 watt audio amplifier and you can see I've got 2 of them. So that's 20 watts total. If you're trying to run 20 watts through this board, obviously you need to make sure the tracks are sufficient, especially in the high power areas, to handle that current. So I'm using 15 volts as a power supply into the board, which I'll be providing through a DC barrel jack. For the testing, I'm doing it through a bench power supply. The 15 volts from here, as you can see, this is the 15 volt layer. And you can see I've made it quite thick, and I'll show you the calculations for this as well in a bit. But that goes to a 12 volt regulator over here for one channel. And it goes to another 12 volt regulator down here for the second channel. So this is the left channel up here, and this is the right channel down here. This is a 12 volt regulator that can deliver up to 1 amp of current, which should meet the 10 watt requirement that we need for this board. What I will make sure to do is not turn the volume all the way up, as I don't want to be overheating these parts as well. I'm using fairly inefficient linear regulators over here, so they might be getting quite hot and there'll be a lot of power wastage on them as well. So first of all, let's talk about the track widths. In any high power circuit, which this is a relatively high power circuit, the width of the track is very important, and you want to make sure that it is not undersized, causing a lot of overheat. So a wider track will mean that you've got lower parasitic resistance of that track. And that means that you're going to waste less power on it, you're going to get less voltage drop on the track itself. So obviously we're running 1 amp through this. KiCad for us as a handy tool that we can use to calculate what track width we need in order to meet that requirement. So if you go to the calculator tool and then go to track width, 1 amp of current, and let's say we can handle a temperature rise of 10 degrees and our current length I've put down as 70, as that's the maximum dimension of my board, but it'll probably be a bit less than this. And you can see this KiCad tool tells me that I need a track width of at least 0.305. Now if I go to my PCB design over here, you can see I've put down some tracks over here before doing my layer, and these tracks are 1 mil thick. So I know this track that's doing the 5 volt rail is going to be sufficient to handle the current without increasing too much in temperature. The 15-volt line is then regulated down to 12 volts, and that is also a high current path, which you can see down over here and also down here. So zooming into the top one to show you in a bit more detail, I've got this fill zone to make a nice thick path to this second layer that I've got down on this board. And then this layer travels down to the power input for this audio amplifier. So there's two inputs, one this side and the other one this side. And obviously the 12 volts needs to get to both of them. The only way I could do this without too much change in the PCB design was using one of the inner layers to do the 12 volt line. And obviously to conduct down to the 12 volt line, I'm using wires. And wires themselves, they can carry a lot of current, but you would need to calculate the requirements if you particularly got high current requirements. KiCad also has a handy tool to calculate how much current a wire can handle. So obviously in this case, you can see I've got 4 wires down here, and this one is 0.6 with a hole diameter of 0.3. So if I go to my calculator tool, 0.6 diameter and a hole of 0.3 can give me a current carrying capacity of 2.4 amps, which would result in a temperature rise of 10 degrees C. Obviously I've put down multiple wires on this board. This is because I have the space, and this will also help to reduce any resistance on that path. So I was talking about some improvements before. I think one of the things I've done a little bit badly on this board is separating the kind of the digital power side and the analog power side. So obviously this has a I2C line, and I've routed it through all the layers. I think I could have done a better job of separating the analog and the digital grounds especially, and analog digital signals, which I might look at an improvement in a later video, depending on how well this board works. One of the things I have done is implement a solid ground plane, which you can see on layer 3 over here, and obviously that goes through the whole board. Now zooming into the MAX 9768, and I can also show you a 3D view of this part. So obviously you got this component down here, and then you have a bunch of capacitors around it. Obviously we went through the calculation of these capacitors and components in the schematic video, so please feel free to check that out if you need to. But as low noise is very important, you need very good decoupling on this part. So I've tried to place the decoupling capacitors as close as possible to the part itself, and also attempted to minimize the ground loop. So one of the improvements I was talking about, I think this capacitor could have been facing this way, and that would minimize the ground loop to this component over here. Obviously I've got this component as well. So there are quite a few decoupling capacitors in here. I did debate adding some smaller value decoupling capacitors as well, but in the end I didn't end up adding them as the cost was going over budget for this video. So that's the decoupling sorted. Now let's talk about the input and the output. The audio signal is coming in from this 1-inch jack over here. I think it's a 1-inch jack. I'm not sure if that's the proper word for it. Obviously the power is coming in through this DC barrel jack. So we've got a left and the right signal. So the left is over here and the right signal is over here. I have a large value electrolytic capacitor, which is doing high pass filtering. So it's removing any DC signal that's coming in. And it's a relatively high value. I think we calculated the cutoff frequency for that filter during the schematic design, during the schematic capture. And then the left channel obviously feeds it into MAX 9768 over here, and the audio output from this part is through this section over here. You can see some large inductors on this board as well as some smaller capacitors, and these are basically filtering out the sawtooth or the high frequency components that are introduced in a Class D configuration. So that's basically all the filtering that's recommended from the datasheet. I have modified some values. For example, this input filter, I reduced the cutoff frequency, this because I wanted to get a value that was available when ordering this part. The inductor and these capacitors are as recommended from the datasheet. And obviously we went through the calculation of these components during the schematic capture. The reason why I've used electrolytic capacitors is that the performance or the capacitance doesn't change very much with respect to voltage. So I think they're good for audio applications like this. And obviously this LC filtering is just recommended from the datasheet. High quality components and good placement is important. I think this design can be improved if we added a kind of a ground plane around this components. And as I said before, we would want to keep the digital and analog grounds different. Obviously I failed to do that on this board, and I think for the next iteration I will improve that. One of the other things you want to do is avoid having crossing analog and digital signals, which I do have on this board. So there are some digital signals, obviously. So this is a digital line, I know. This is the I2C line, which I'm not going to be using on this board because I do have a variable resistor for the volume control. So going on to the I2C line, obviously I've got the I2C line going from here. I think for this we want to turn the 3D view off. So it goes through these components here, then we've got some configuration that we need to select, which can turn the I2C communication on or off. So I've left the option open just in case we wanted to play around with that mode. And then it goes around from here down to these two pins here. So if I wanted to connect this board up to a microcontroller, I will be able to. And in order to do that, I will need to change the configuration on this and these pads over here. So this pad changes the address for the I2C, and this pad basically you can select if you want it in analog volume control or digital volume control. So the digital volume control is done with the I2C. So that is basically main aspects of this board covered. Another thing that was needed for this is a 3v3 regulator as well. So you can see that that's down here, and the 3v3 regulator is fed with the 15 volt line that's coming from here, the DC barrel jack. And for that, obviously the component selection you'll be able to see on my schematic video, but it's a AMS 117-3.3. The 3v3 line is not going to be carrying a lot of current. I think I worked it out to be less than 10 milliamps. But you can see I've got some separated lines that are going to the individual audio amplifier chips, and then I've got some selection things here as well. But the speakers I have, they all are RCA connectors, so this should be good enough for that. And one of the other things you might notice, I've got some through-hole resistors on this, and this is to fine-tune the gain of the two audio amplifiers if I need to do it. I think in the next iteration I'm going to basically delete them because I'm not entirely happy with having these long tracks that are unterminated. Which if you've got 20 kilohertz, which is not the highest of frequencies, but again, it's not good design practice to have long tracks like this that are just floating. Another easier way I could have done this is added a 0805 resistor over here, but I don't have any resistors to hand. I only have through-hole resistors to hand, so this is why I put these on. I think that covers everything for the board. Obviously you've got the logo here, which is on full screen, and hopefully it looks quite neat. You saw an assembled board at the beginning, but let me walk you through the actual board and what it looks like and how the connectors look when it's fully built up. So this is the board. You can see I've got the RCA connectors, my audio input over here. So this is a 1-inch jack. I think it's 1 inch roughly. We've got the RCA connectors, like I said before. Got the DC barrel jack, which I've ordered and it's still to arrive. And I've got the various input connections that I might use for this board down here. And the two regulators that I pointed out previously. And the two Max 9768 ports. Obviously got the left channel on the top and the right channel on the bottom. I've got my input with the two capacitors. So that's it. I'm going to build it up in the next video and we'll test it out. Thank you for watching my video today. Hopefully you enjoyed this. If you have any suggestions for me or if you have any comments, please leave them in the comment section below and I'll be happy to answer any questions as well. So let me know. Bye for now.